Hi, everybody. My name is Daniel, and today I'm going to talk about enabling memory tiering in CacheLib. This work was done with my colleagues Sergey, Igor, and Tomas, and we're from Intel. So give a brief overview of our talk today. We're going to introduce memory tiering, why we need it. We're going to talk about CacheLib, what CacheLib is, how do we use it, and how do we add heterogeneous memory support. We're going to give a performance analysis, some solutions to the overhead that we measured, and some future ideas that we have. And then we'll wrap things up. So why memory tiering? We have new memory technologies such as CXL that offer a wide range of use cases. So we could do memory expansion in a single server, or we have dynamic memory pooling across nodes. So CXL and PMEM can reduce the cost of infrastructure. CXL can increase your memory utilization, so we can make use of memory that was previously a memory device that was previously underutilized, or we can use persistent memory to offer larger capacity at a lower cost compared to DRAM. So this figure on the right here shows the hit ratio versus the cache size. And we took this from the graph cache leader workload from CacheLib. And we show here how with a reduced, we show here how that CXL and PMEM lead to a reduced total cost of ownership because we've replaced that DRAM with some amount of CXL and PMEM. And on the other hand, we show that memory tiering can give us higher performance in terms of hit ratio, because if we keep the cost the same, but we can add more memory to the system, then we are increasing the hit ratio to the cache, which lowers the amount of times that we have to go back to our backend storage system or our slow backend server, and increases the performance of our application. Okay, so CacheLib was developed by Meta and released as open source software in late 2021. And like I mentioned, it's a caching library. It can run in process, or you could build it up a part of a network stack if you need remote access. In CacheLib, we have a find and allocate API where find takes in a key and then it returns you this item handle here. The item handle, if it's valid, then we can print out the memory or print out the data. And we also have the ability to use callbacks. So once we retrieve this item handle, get the data, then we can go ahead and use another method once that data is ready to do it. So it's very extensible, and it's written in C++. So CacheLib is organized into different memory pools, and then each memory pool is a set of independent allocation classes. So each independent pool contains its own allocator, and then each pool is divided into allocation classes. Items are organized logically by their respective size, and these allocation classes follow a geometric sequence. For example, the default in CacheLib is size, class 1 gets size 96 bytes, class 2 gets 144 bytes, object size in between 96 and 144. And so this is configurable, tunable to your application. If you're using larger objects or smaller objects, you can figure out what class size works best for your application. And then each class contains its own independent LRU list. This LRU list, when the class is full, so a class is assigned a set of slabs. When that class is full, it will evict the LRU item from that class here. So this LRU list here is on a per class basis. Okay, so what we did to enable heterogeneous memory is we took the DRAM tier and we added memory tier 0 and memory tier 1 as byte addressable memory spaces. We changed the configuration API to allow this configurable memory tiers. And what's great is that this is totally transparent to any applications that are using CacheLib. So the high level API doesn't matter if the objects are in memory tier 0 or memory tier 1. And we were able to reuse some of the existing eviction mechanisms to evict items from tier 0 to tier 1. And then, of course, we still can have this backing flash layer. We're still working on promotion between the tiers, so moving these objects here, but we have eviction down. Now, feel free to go ahead and check out our development branch at PM+CS'22 on GitHub. It's up there for you. Okay. Our configuration API, so to enable CacheLib, we just initialize the cache, and with this configuration, we've added configure memory tiers. We can configure memory tiers from file. So if we pass in some shared memory, or we could pass in our pmem file. This is on a fsstacks device. And we also set the ratio. So we could set ratio 1 to, so we have 2 parts pmem for every part DRAM. In this case, we get a 12 gigabyte cache where 4 gigs is DRAM and then 8 gigs is pmem. Pretty straightforward. Now, the multi-tier memory organization looks a lot like the single-tier DRAM instance. And this is actually, the same architecture as before. It's just we've duplicated that DRAM memory organization to the pmem. We insert new items into DRAM, and the individual objects are moved between tiers on eviction. So this eviction process, so when an item is evicted from allocation class A, requires locking the LRU list in this source in A while we do the entire eviction process to our pmem. See here as it goes. And this is actually a source of some overhead. So we'll go into some more details later on that. But first, we want to give our initial benchmarking and system configuration. So we have Xenon processors with the system has 256 gigabytes total memory, and then we use 8 256 gigabyte set of Optane DIMMs, CentOS with Linux kernel 5.17. We compile CacheLib with GCC version 8.5, and we enable hyperthreading and turbo. I've also pasted here our benchmarks for both the follower and the leader used from CacheBench. So CacheBench is the benchmarking application for CacheLib that's included in the repository as well. Okay, so our initial benchmarking results for these Lookaside cache workloads turns out that our multi-tier instance underperformed compared to the single-tier DRAM and single-tier pmem instance. So our multi-tier, we took 50% DRAM and 50% pmem. Total cache size is 8 gigabytes. And in our leader workload has 0.42 hit ratio. So on every cache miss, we issue an allocate to that item so that on future reference to that item, it becomes a cache hit. So for the lower the hit ratio, the more allocations there are. So the leader workload really stresses the allocation path, whereas the follower workload has a high hit ratio. It does relatively little number of allocations just while the cache is warming up. And then the rest are read requests. So the follower workload is stressing the lookup path more, and the leader workload is stressing the allocate path more. Higher throughput is better, and these are numbers kind of baseline to DRAM single tier instance. PMEM is just under 60% of the performance, and we don't even get to have performance in multi-tier instance. Ideally, we would expect it to be somewhere in between. The same case kind of in the latency, our multi-tier latency numbers are kind of on par with what we would expect, except in the leader workload. We have pretty high P99 latency. So that tends to point that there's some pathological allocations that are really slowing things down. When we looked at VTune, we used the hotspot analysis, and this is just a snapshot of our report summary that we got. We saw that the spin mutexes are waiting a significant amount of time, and we tracked this down to the LRU locks. We saw that there's a high amount of LRU lock contention, and so we thought, hey, let's do whatever we can to reduce the lock contention. There's a neat little option in CacheLib configuration called try lock update. And this controls whether we update the LRU list on a lookup. So if it's set to wait, then we always update, even if we're waiting to acquire that lock of the LRU list lock. If we're set to bypass, then we update only if there is no contention. We'll bypass that lock if we fail, or we'll bypass updating the LRU list if we fail to obtain that lock. Now, in terms of the leader workload, we do see a pretty significant improvement in performance because we're seeing a lot more allocations that are holding the LRU lock for longer. And by enabling try lock update, the lookups no longer have to contend as much for that lock. We don't really see much of a difference in the get throughput in the follower workload because this workload is already stressing the lookup path enough, and it's not doing too many costly allocations. But we do see in our leader workload that the P99 latency is reduced when we have the try lock update enabled. So that points us to this idea that the allocations still are causing more contention in the LRU queues. So why is this, and what happens in the difference between single tier and multi-tier evictions? Well, we know that these evictions cost more in multi-tier environment because our critical section is longer. Eviction in the single tier, we find the item and recycle it immediately. Versus the multi-tier, we find the item, then we have to allocate the new item in the next tier. This might cause a recursive eviction where we also have to make space for that item again. So we get this recursive eviction process. Then we have to copy the data from our source tier to the destination tier. And finally, we can return up that free allocation slot. So we came up with a couple of ideas to decrease the eviction overhead. We created a background evictor thread that preemptively clears out items so that we don't have to perform those allocations on the critical path. We tried to insert items into the first free tier. So multi-tier, if there's no slots in DRAM, let's go to PMEM. allocate there. And ideally, this can be combined with the background thread because you want your hot data or your newly allocated data to land in your first tier and not spill over into PMEM as often. You want to let your cold data kind of reside in PMEM. And then we experimented with decreasing critical section length. So this idea that once we remove the item from the eviction queue, let's drop the lock and evict to the next tier. And this idea is that evicting an object should be lock free once we have our eviction candidate. We shouldn't have to contend with the LRU eviction queue once we know who the LRU is. And a couple of ideas that we have worked in progress is scalable, more scalable eviction policy as well. So inserting first free and background evictor actually came up with some interesting results. So first free is the idea that we can use the first available allocation slot might not necessarily be in tier 0. Problem with this is that the cache should have the hottest items in tier 0 in our initial tier. And moving those hot items that are allocated into PMEM on the spillover is difficult because the hot items, it's difficult to acquire the locks needed to promote that item into tier 1. There's already a lot of contention for those items. They're being heavily requested. It actually will decrease our performance. But if you look at our first free tier, the red bar here, we get almost 80% of the performance of a DRAM in terms of a DRAM single tier instance in terms of throughput. Now, in the leader workload, it's about 75% of the DRAM single tier performance. So compared that back with the PMEM, we're doing pretty good. Now, the background evictor thread preemptively moves the cold items to the next tier, and it's done in batch. So we want to keep 100 allocation slots open, or we want to keep like 1% of the memory free. This actually has a negative effect since we add even more contention to the LRU locks under high throughput. So we see that our with our background evictor thread, we have a reduced performance compared to with the background evictor thread off, this BG off versus BG on. The throughput is lower. So we have some optimization and some work to do there. Next, we looked at decreasing the critical section length. So this is the idea that the LRU lock for tier 0 is dropped once we have an eviction candidate. And the performance turns out to be really good. Our reduced critical section, these blue bars here, compared to the original, we get about 67% of the performance of a DRAM single tier instance, which improves over the PMEM instance and significantly improves the performance compared to having that longer critical section in the follower workload. And then even more so in the leader workload, because the leader workload was doing a lot more allocations. And so it was doing those longer, more costly allocations more often compared to the follower. And so that's why we see even a larger jump. This is more than 4 times improvement in the multi-tier with reduced critical section compared to our original implementation. And we can see now here that with background evictor off or background evictor on, there's no we don't have a negative impact in terms of throughput. And in terms of latencies, we tend to see lower latencies in multi-tier configuration with our background evictor on and the reduced critical section. compared to our PMEM instance. PMEM instance, this is the original PMEM instance, and then our PMEM instance with reduced critical section. So one thing to note here is that we are seeing higher P99 latency with our reduced critical section implementation. So there is still something pathological that's going on there at the 99th percentile that we've added in that we need to investigate further. But our initial results look pretty good. And you can see in our leader workload, the leader workload actually has higher P99 latency compared to PMEM original implementation. So in our multi-tier configuration, we get a higher P99 latency there. So still some optimization to do with some of the cases where we perhaps fail to do the eviction, we have to reacquire the locks. But really a good step in achieving this performance parity and actually outperforming a single tier PMEM instance. That's where we would expect to be. So future directions and ideas is to scale the eviction policies. We could use containerless policies. So if we did random sampling, similar to the idea in Redis, we don't need to have a container that we need to lock every time if we just do some sampling every time we need to do an eviction. Of course, we have to add recency and frequency information on an item. So there could be some metadata overhead there. We're thinking about partitioning the LRU lists. So this is kind of like what the current Memcached LRU design is like. The 2Q implementation has hot, warm, and cold regions that are all under the same multi-list data structure. And if we were to partition those hot, warm, and cold regions out into independent structures so that you can lock the hot region while you're doing a lookup, and then the evictions can lock the cold region, and so you don't have you can reduce your contention there. So with that said, we just like to conclude that memory tiering with CXL and PMEM increases memory capacity for a lower cost compared to DRAM. And it's really especially applicable in these caching applications where more memory translates to higher hit ratio. But as we've seen, the software support needs to consider these techniques to mitigate the data movement overhead that we see on the critical path. So we looked at a couple of ideas like choosing the fastest allocation path, background data migration, or reducing the critical section. So we're looking at more ideas, and we believe that we can get to multi-tier DRAM PMEM performance parity to a single tier DRAM instance. That's our goal. And that's where we're headed in the future. So I'd like to thank you for taking your time to listen to this talk. And if there are any questions, reach out to us. Be happy to answer them and have a discussion. Thank you.